Welcome to the next lecture on modulation techniques. Today we will look at some of the important linear modulation techniques. First, the outline of today's lecture. We will summarize briefly what we have learnt so far. Then we will look at an important class of modulation techniques called the linear digital modulation techniques. In particular, we will look at the binary phase shift keying or BPSK. Then we will talk about the differential phase shift keying or DPSK, followed by quadrature phase shift keying or QPSK, offset QPSK, an interesting variation of QPSK, and the pi by 4 QPSK. So this is the brief outline for today's lecture. A brief recap. In the previous classes, we talked about the power and the bandwidth efficiencies of modulation techniques. We also discussed line coding. We talked about the problem of inter-symbol interference, which is caused when your bandwidth is limited, which leads to the spreading of the pulse and different pulses interfere. And the important method of pulse shaping, wherein we reduce and mitigate the problem of inter-symbol interference. Now let us switch gears and move over to digital modulation, and we remember from last class that there are some important advantages over analog modulation techniques. First of all, there is greater noise immunity in the case of digital modulation techniques and robustness towards channel impairments. It is found that most of the digital modulation techniques perform better in fading environments, which is the normal scenario in most of the wireless communication scenarios. Then again, we have easier multiplexing of various forms of information like voice, data, video, multimedia kind of services, where digital modulation technique immediately comes to the rescue as opposed to analog schemes. The world has shifted to the digital modulation techniques, and today very few mobile communication services even think of adopting analog modulation. In this slide, we will look at briefly the different types of digital modulations. You can classify them into linear, non-linear and spread spectrum techniques. In linear modulation techniques, which we will discuss today in detail, they are bandwidth efficient, useful for accommodating more users in a limited spectrum. How do we choose one modulation scheme over others? We will discuss that in one of the subsequent slides. In the nonlinear techniques, we have likes of FSK, GMSK, MFSK. GMSK is used in the GSM mobile phone standard. We will talk about it in one of the later lectures. And of course, the spread spectrum techniques, which are omnipresent in the 3G standards. Today we will focus on only the linear techniques, namely BPSK, QPSK, offset QPSK and pi by 4 QPSK. The three basic signaling schemes that we know are the amplitude shift keying, the frequency shift keying and the phase shift keying. Our emphasis today will be on phase shift keying. Please note that how do you choose a modulation scheme? You have so many choices. How do you evaluate one with respect to another? What are the basic criteria based on which you decide for one modulation scheme versus the other? One is the optimal design of the receiver and how easy or difficult it is to implement the receiver. Then the performance, which is the bottom line. What is the probability of symbol error of the receiver given the same signal to noise ratio? It is found that some of the modulation techniques perform better with respect to the other ones. And of course, the spectral properties of the modulated signals. So you have the complexity of the receiver, the probability of symbol error, and spectral properties of the modulated signals as the three balls that you have to juggle in order to choose and pick one particular modulation technique. Now let's briefly revisit a model of a digital passband system. We always start with a message source. It could be a voice digitized, or it could be an image or video or fax, and we denote it by MI. Then it passes through a channel encoder. By design, we have skipped the source coding part, assuming that this is incorporated in here. So channel coder puts redundancies in a known manner so as to overcome the effects of noise and other channel impairments, and we get SI. Then it is passed through a modulator, which must make use of a carrier, and then sends out a waveform in the time domain. This waveform is passed through the channel, wherein the various channel impairments and noise come into play, and what we receive is x of t, which is very different from the s of t. It passes through a demodulator. The first job of the demodulator is not only to get the possible estimate of the message, but it also creates some kind of an limitation on the effects of noise. So it is a way, a technique to overcome the effects of noise introduced in the channel. What we get back is x. Then you undo the channel coding part, which was to overcome the effects of noise here. You do a channel decoder, and then finally get an estimate of MI. A quick revisit on the geometric representation of modulated signal. If there are m possible signals, and the modulating signal set S can be represented as S is equal to S1t, S2t up to SMT. For binary scenario, m is equal to 2. So you have only two symbols. For higher level memory modulation schemes, m is greater than 2, and the signal space may be represented as a vector space. What does it mean? Any point in vector space may be represented as Si as a summation I is equal to 1 through n. N is the dimensionality of the space, Sij phi I, where phi I t is the basis signal, which has the property that some integration phi I t, phi j t dt from minus infinity to infinity is 0 for I not equal to j. Each basis signal are orthogonal, and each base signal is normalized to have unit energy. So what it basically means is that your signal set may be represented as points on the signal space. The dimensionality is n, and m represents the number of symbols. Let us now begin our study of linear modulation techniques. What is linear modulation technique? In linear modulation schemes, the amplitude of the transmitted signal S of t is varied linearly according to modulating signal. It is bandwidth efficient and used in wireless communication to accommodate more and more users within a limited spectrum. The modulated signal may be represented as St, real part of A, which is the amplitude, Mt, e raised to power j2 pi fct. Here fct, fc is the carrier frequency. If you expand it out, it can be written as m t cos 2 pi fct minus n I sin 2 pi fct. M subscript r is the real part and mi is the imaginary part. Mt can be written as follows. it requires linear amplifier at RF, which is costlier, and some of the popular schemes within the linear modulation techniques are QPSK, offset QPSK and pi by 4 QPSK. We will talk about each of them as well as the BPSK in detail today. So what is binary shift keying? Let us consider two possible signals, M1T and M2T. Now 0 represents M1T and 1 represents M2T. So if I have a strings of 1s and 0s, I send M1T whenever a 0 is encountered and M2T when a 1 is encountered. But in our case, binary phase shift keying, both signals M1T and M2T has a 180 degree phase shift. So BPSK transmitted signal may be represented as MT under root 2 EB over TB cosine 2 pi FCT plus theta C. So in effect, the BPSK is equivalent to double sideband suppressed carrier amplitude modulated waveform, where cos 2 pi FCT is the carrier. Fairly simple, robust, but you have only one bit per symbol. How does the bandwidth of the BPSK look like? The BPSK signal can be expressed in complex envelope form as follows: real part G BPSK T e raised by j 2 pi FCT, where G BPSK T is the complex envelope of the signal given by under root 2 EB over TB MT e raised by j theta C. The power spectral density of BPSK can be calculated to be of this form. Right. It is more interesting to plot this out and see how it looks, because part of the job of a good modulation technique is to have good spectral properties of the modulated waveform, because that has a direct implication on the design of the transmitter and receiver. So here graphically we have the power spectral density of a BPSK signal. Please note that there is a main lobe and there are side lobes. The main lobe is centered at FC and the nulls are at FC plus RB, FC plus 2RB and so on and so forth. So suppose you intercept an unknown signal and plot its power spectral density, and it looks something like this. Possibly this is a BPSK. We will soon see QPSK power spectral density also looks similar, except that these nulls, instead of being at FC plus RB, FC plus 2RB, it's more like FC plus RB by 2. Now if you have a alpha is equal to 0.5 raised cosine filtering imposed on it, then you have a much narrower main lobe. So the purpose of this raised cosine filtering is to band limit the modulated signal. We will soon see the problems with QPSK when you put this raised cosine filtering. Basically band limiting leads to certain problems. Let's talk about the receiver. BPSK uses coherent or synchronous demodulation. What does that mean? I must have the knowledge of the carrier and the phase also. The received BPSK signal can be expressed as S BPSK in time domain equal to MT under root 2 EB TB cos 2 pi FCT plus theta. Theta C is the phase of the carrier and theta ch is the phase shift introduced due to time delay in the channel. So what you receive is theta equal to theta c plus theta channel. The bandwidth of QPSK is 2RB is equal to 2 over TB. Now the probability of error is given by Q function under root 2EB over TB. This is a standard expression. So we quote here without the derivation. Let us now briefly talk about the BPSK receiver with carrier recovery circuit. So here is your empty cos 2 pi FCT plus theta, which we saw in the previous slide as your BPSK modulated signal. That is first passed through a square law device, which generates cos squared 2 pi FCT plus theta. Now the moment you band pass filter it at 2 FC, you get cos 4 pi FCT plus 2 theta. Pass it through a frequency divider to recover cos 2 pi FCT plus theta. You have already empty cos 2 pi FCT plus theta, take it here, multiply, you get back this. Integrate and dump, you get m of t as a DC value. Right? So this is the simple BPSK receiver. Now the BPSK receiver requires the knowledge of the phase. You have a slight variation called the differential phase shift keying or DPSK. DPSK is a non-coherent form of phase shift keying. DPSK receivers are easy and cheap to build and therefore used in wireless communications. Let us have an illustration with an example. So you have your message MK, these are bits clearly, and then the differential output is represented by D subscript K. And here we have written down D subscript K minus 1 and at the kth instant D subscript K. So if you look, if there is a 1 here, there will be a 1 here, 1 here, 1 here, 0, 0. So they are just shifted version of each other. So dk minus 1 row is shifted to the right with respect to the row of dk. Now the rule for differential encoding is very simple. Dk is mk XOR dk minus 1 not function. What does it mean? That if you have a 1 come in, then you don't change the output. If you have a 0 coming in, then change dk. 0 comes in, change from 0 to 1. 1 comes in, don't touch 1, let it be 1. 0 comes in, change the 1 to 0. 1 comes in, don't change the 0, let it remain 0, and so on. Fine? So the probability of error in the differential phase shift keying is given by half e raised power minus EB over N naught. Let us talk about the DPSK transmitter and receiver. So the transmitter is fairly simple, exactly doing the encoding process we discussed a while back. Input data comes in, it's a sequence of 1s and 0s, it's binary. There's a logic circuit and you get a decay. If you pass it through a delay, you get dk minus 1. All you have to do is, if a 0 comes in, flip the decay, if a 1 comes in, leave it untouched and you get decay. Now you have a product modulator, right? So make it plus a cos 2 pi FCT for 1 or minus cos 2 pi FCT for 0 and you have your DPSK. Let us talk about the receiver. You have the DPSK signal. First you band pass filter it. You have a logic circuit, and then you had a delayed version by TB. Multiply, integrate and dump to get the DC part out, threshold, and get the demodulated signal. Fairly simple. This is the added advantage why DPSK is popular. Very simple design, and you do not have to recover the phase because it is simply differentially encoded. Of course, it comes with a price. There is about a 3 dB loss in performance. Now let us look at the big brother of BPSK, which is the QPSK, or quadrature phase shift keying. QPSK has twice the bandwidth efficiency of BPSK, so we are actually going to send 2 bits per symbol as opposed to 1 bit per symbol in BPSK. The phase of the carrier takes one of the equally spaced values 0, pi by 2, pi and 3 pi by 2. The QPSK signal is given by S QPSK T under root 2 ES over TS. ES is the energy per symbol, T subscript S is the symbol time, cos 2 pi FC plus one of the 4 phases. The probability of bit error in an additive white Gaussian noise channel, or AWGN, is given by the Q function under root 2 EB over N naught. Similar to BPSK, QPSK can also be differentially encoded to allow non-coherent detection. Let us now talk about the constellation diagram of QPSK. So clearly you have the in phase I and the quadrature Q components. This could be your cos omega ct, this could be your sin omega ct, or any 2 orthogonal functions. We can map 0 0, 0 1, 1 0, 1 1, or 0 0, 1 0, 1 1, 0 1 in one of the 4 symbols. The other possibility is pi by 4 rotated version of this. The one on the right hand side is a more popular implementation. Let us talk about the spectrum of QPSK signal. The power spectral density of QPSK signal using rectangular pulses can be expressed as follows. It looks very similar to that of the BPSK, except the nulls have shifted. This is in terms of EB, here it is in terms of ES by 2. So if you plot the normalized power spectral density on the y axis and frequency on the x axis, you see that it is again centered at Fc, but the first null appears at Fc plus Rb by 2. Had this been a BPSK signal, you would get Fc plus Rb, and so on and so forth. If you use a raised cosine filter with alpha is equal to 0.5, you kind of shrink the main lobe. Clearly, there will be problems when you do so. The problem comes because in QPSK you have occasionally 180-degree phase shift, and in those cases when you are passing through the 0, then band limiting the process kills the signal. Let us talk about QPSK transmission and detection techniques. First, the QPSK transmitter. You have an input data Rb. This is a string of bits, ones and zeros. you have to take 2 at a time, because the job of QPSK is to take 2 bits at a time and encode it. However, what you do is you have a serial to parallel converter and you split the bits, right, and then you have a local oscillator, in phase, quadrature, add, band pass filter it and send out the QPSK signal. If you have to do the receiver part, you have the receive signal, band pass filter it, you must have a carrier recovery circuit as discussed before, in phase, quadrature, multiply, low pass filter it, also have a symbol timing recovery, decision circuit, multiplex, because you get from arm 1 signal for one of the bits, the second bit multiply, and for every symbol you get in, you get 2 bits out on this side. So, very simple logical QPSK transmission and detection circuits. Now, let us look at one variant of QPSK. It is called the offset QPSK. Why do we need it? The amplitude of a QPSK signal is ideally constant, because if you look at the constellation diagram, all the 4 points are located on a circle. So, they are equidistant from the origin, and the distance from the circle tells you or gives you an idea about the amplitude. When pulse is shaped, they lose the constant envelope property. Clearly, you are doing pulse shaping. So, it is not a rectangular pulse anymore, it is pulse shaped. Now, in QPSK, you have no control over what symbols will be transmitted. So, sometimes you have a transition from S0 to S1, which is 90-degree phase shift, or sometimes from S0 to S2, which is 180-degree phase shifts, basically pi radians. And then a phase shift of pi radians can cause the signal envelope to pass through the 0 for just an instant. Right? Now, any non-linear amplification of the 0 crossings brings back the filtered side lobes. If you remember in the previous slides, once you do a raised cosine filtering, you eliminate the side lobes, you shrink the main lobe. But what is happening is, because of the pulse shaping, you are just forcing the 0 crossings to go to smaller values, and when you have to do a non-linear amplification of the 0 crossings, you have again the side lobes appearing. In effect, you are causing spectral whitening. You are defeating the purpose of cosine filtering or any of the pulse shaping techniques. So, let us look at the constellation diagram. Suppose you have the standard QPSK constellation diagram. X axis is the in phase, y axis is the quadrature. All the 4 symbols are located on this circle. Now, suppose the first symbol that is transmitted is S1. So, here we label S0, S1, S2 and S3. Now, depending upon what bit stream is coming, it is possible that you send the next symbol as this one. So, from here to here. So, in effect, what happened is we had a pi radian phase shift. It is a chance. It was possible that the next 2 bits that come in makes this appear here. So, here in this case it is only a 90-degree phase shift. However, if I am here, I can go to another 180-degree pi radian phase shift. Again, I am jumping. So, in QPSK, I can either have a 90-degree phase transition or a 180-degree phase transition. The moment I have a 180-degree phase transition, I am in problem. I have to do something to limit this pi radian transition, and the answer comes in terms of offset QPSK. Because the moment I have a nonlinear amplification of the zero crossings, I bring back the filtered side lobes. That is the basic problem with QPSK. So the solution is fairly simple. You generate two time offset waveforms, one for the in phase and one for the quadrature. So let's say for the in phase I have the following waveforms: 1 0 1 0 0 0 1 0, and for the quadrature again I have 1 0 1 0 1 1 1 0. I have taken two arbitrary things. But what is important is in QPSK I would have sent this one to in phase arm and this one to quadrature. I do the same thing, except this time for offset QPSK I shift my quadrature bit stream by a small amount given offset, right? So this offset will ensure it's in between a bit, that phase shifts can never be 180 degrees. They can be at most 90-degree phase shifts. Because even though QPSK is dealing with 2 bits at a time, at any time instant, 2 bits cannot change at the same time, because I am only feeding one new bit per bit interval. So what are the differences between offset QPSK and your regular QPSK? They are almost similar, except for the time alignment of the odd and even bit streams. In QPSK signaling, the bit transition of the even and odd bit streams occur at the same time instant. However, in offset QPSK, the even and odd bit streams are offset in the relative assignment by 1 bit period, which is half symbol period. The offset QPSK does not cause the signal envelope to go to 0, simple. There is no more fear of a nonlinear amplification of the zero crossing, thereby reducing the regeneration of the filtered side lobes at high frequency. What are the similarities? The signals are identical, hence both signals occupy the same bandwidth. The staggered alignment of even and odd bits does not change the nature of the alignment. Advantages of offset QPSK. The first and the foremost is the maximum phase shift of the transmitted signal is limited to 90 degrees. That was my biggest fear in QPSK. Possibly there were several 180-degree phase shifts. But since 180-degree phase shifts have been removed in this case, pulse shaping does not cause the offset QPSK signal envelope to go to 0. Hence, nonlinear amplification does not generate high frequency side lobes. Thus, the spectral occupancy is reduced, allowing more efficient RF amplification. So, your receiver design also improves. Now, let us talk about pi by 4 QPSK. This is a compromise between QPSK and offset QPSK. In QPSK, there is a possibility of having 180-degree phase shifts and occasionally 90-degree phase shifts. In offset QPSK, you have at most 90 degree. How about reaching a compromise? How about 135 degrees phase shifts? So, the maximum phase change is limited to 135 degrees, though it can be less, as compared to 180 degree for QPSK and 90 degree for offset QPSK. Hence, the signal preserves the constant envelope property better than the band limited QPSK. This can be demodulated in a coherent or non-coherent fashion, thereby simplifying the receiver design greatly. Please remember, apart from the probability of symbol error and the spectral characteristics of the modulated signal, any modulation scheme must also have a very simple transmitter, modulator and demodulator design. Here the receiver design is greatly simplified. Now the added advantage thrown in is in the presence of multipath spread and fading, this pi by 4 QPSK is found to perform better. It just happens. When differentially encoded, QPSK is called differential QPSK and pi by 4 QPSK is called d pi by 4 QPSK. Now let us briefly discuss some of the pi by 4 QPSK transmission techniques. In this slide we have the block diagram of the pi by 4 QPSK transmitter. Clearly we have the bit stream coming in MK, where you have again a serial to parallel converter. I split it up, I get M in phase K, K is the time index, and MQ quadrature, K is the time index. Then I must do some kind of a signal mapping. What are this I sub K and Q sub K? We will talk about these two in the next slide. So in the next slide we will talk about what exactly is the signal mapping doing. But once you have this IK and QK, you low pass filter it, and then you have the in phase cos omega Ct or cos 2 pi f Ct and sin omega Ct with a negative sign. You get the in phase component and the quadrature, add them up, amplify and shoot it off. You get the pi by 4 QPSK signal. So what is important in this slide is to understand how you take this bit stream, and having divided it into the in phase and quadrature bits, do the signal mapping so that you get IK from MK in phase and QK from MK quadrature. So the IK is IK minus 1 cos phi k minus QK minus 1 sin phi k. That is how you do the signal mapping. And QK is sin phi k given by IK minus 1 sin phi k plus QK minus 1 cos phi k, where phi k itself is, theta k minus 1 is equal to theta k minus 1 plus phi k. What are these theta k's and theta k minus 1s? Theta k and theta k minus 1 are the phases of the kth and k minus 1 symbols. The phase shift phi k is related to the input symbols M in phase k and M quadrature k. These M's are the bits we saw in the previous slide coming here, which is done, goes through the signal mapping block to give you I subscript k and Q subscript k. So what is the waveform? The waveform in the time domain for pi by 4 QPSK is IT cosine omega Ct minus Qt sine omega Ct. It comes from passing it through the LPF, multiplying with cos and then adding it up. So we are here IT and Qt. IT is given by summation from k is equal to 0 to n minus 1 I k p t minus k ts minus ts by 2, and similarly Qt. Now let us come to the different kinds of pi by 4 QPSK detection techniques. There are 3 detection techniques, and we will briefly go over all of them from the block diagram perspective. The first technique is the baseband differential detection. Please note, the pi by 4 QPSK essentially works on 2 constellation diagrams. So that is a good way to understand these things. So for every bit that comes in, it alternates between the two constellation diagrams, and in that case it's only possible to have a maximum phase shift of 135 degrees, provided the two constellation diagrams themselves are offset by 130 by pi by 4 only. Okay. So if you have a diagram, so let us look at how pi by 4 QPSK looks like. Suppose we have two constellation diagrams. So you have this as in phase and quadrature, and here you have 4 points, and then you take another one. Again, this is your in phase and quadrature, and this time you have pi by 4 shifted versions. Suppose you merge them together. What do you get? You get points from one and points from the other. Please note that if you have the possibility of switching between case 1 and case 2, then regardless of where you are, you can go from here to either this one, or this one, or this one, because once you have sent this one using constellation 1, in the next symbol interval you can only use constellation number 2. But constellation number 2, if you see, gives you possibility here, 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 here. Constellation 1 gives you here, 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 here. So regardless of where you are, suppose you are sitting here, the next instance you can only work at pi by 4, or here, or here, or here. So the maximum jump is 135. So you can go from here to here, here to here, here to here, or here to here. Whereas suppose you are sitting in this location, next time you can either go here, or here, or here, or here. Similarly, if you are sitting here, you can either jump here, jump here, right? Jump here. So the point that is being made is, regardless of whichever symbol point you are, the next transition cannot be 180. It can be maximum 180 degree, sorry, maximum 135 degree transition possible for pi by 4 QPSK. So if you write it, in regular QPSK, it's possible to have 180 degree phase shifts. In your offset QPSK, it's only possible to have 90 degree maximum, and here you have a compromise between QPSK and OQPSK, giving you 135 degrees. So it's a very interesting way. The added advantage, of course, we have seen is it performs really well in the case of fading channels. Now let us go back and look at the pi by 4 QPSK detection techniques. There are three types of detection techniques which will essentially use the philosophy of using two constellation diagrams offset by pi by 4. These are the baseband differential detection, the IF differential detection, and FM discriminator detection. Let us talk about the baseband differential detection. You have this pi by 4 QPSK RF input coming. Of course, you must band pass filter it first, because I want to only focus on the signal of interest. Then pass it simultaneously to two multipliers. One multiplies it with 2 cos omega ct and the other one with minus 2 sin omega ct. Low pass filter it and sample at maximum output for every T of S. You do this for this branch as well as for this branch, right? If you do the maths, you will see you are getting wk minus 1 plus zk minus 1. These pertain effectively to the two constellation diagrams. Pass it through a decision device, take an input on which bit was being sent of the two bits on the in phase and the quadrature, multiplex it, and you get back the baseband differential detection. The other technique, so this is method 1. The other technique is the IF differential detector. Here the game is a little simpler. You pass the input through a band pass filter, and then you have a 90-degree phase shift cos 2 pi f ct sin 2 pi f ct, low pass filter it, again sample at max output for every symbol duration, decision device, multiplex and demodulate. Where is the complexity shifted? Into the decision device now. So the decision device has to work harder. This is your method 2. Please note, here the modulated IF signal is fed. Therefore, it is called the IF differential detector as opposed to the earlier one which worked at the baseband. And the third method is the FM discriminator method. Here you have the pi by 4 QPSK signal coming in. Again, begin with have a band pass filtering, limiter, and then you have a FM discriminator, integrate and dump. Here you have a 4-level threshold detector which takes the decision, parallel to Sealier converter, and you get the demodulated waveform output. So these are the three popular methods for the detection of pi by 4 QPSK signals. Let us now summarize today's lecture. Today we focused on linear digital modulation techniques. We looked at both the modulating part and the demodulating part. We started off with binary phase shift keying. We looked at the spectrum of the binary phase shift keying, the good generators for BPSK, and also demodulators. Then we focused on the differential PSK and looked at an example as to how to carry out DPSK, followed by quadrature phase shift keying, one of the very popular techniques. We then talked about